Hi, this is Alex from devstories.eu. AlphaFold, Protein Structure Prediction, Episode 19 of 21. Sometimes the GPU is not actually slow at doing math. It is just spending all its time waiting for the CPU to give it the next instruction, leaving your profiler full of massive gaps of white space. The solution to this problem is kernel fusion and GPU optimization. According to the ScaleFold paper, training the AlphaFold model requires launching over 150,000 individual operations per step. Most of these are memory-bound kernels, like small layer norms or fragmented element-wise operations. Every time the CPU tells the GPU to run a PyTorch operation, there is a launch overhead. When you string together 150,000 small operations, that overhead completely eclipses the actual math. Look at AlphaFold's Multi-Head Attention, which takes about 34% of the total training step time. It is not standard attention. AlphaFold adds a specific pair bias term to the logits matrix right before the softmax operation. In default PyTorch, this creates a chain of separate events. First, you launch a kernel for the batched matrix multiplication. The GPU reads the data from global memory, does the math, and writes the result back. Then, the CPU launches a second kernel to add the pair bias. The GPU reads the matrix back from memory, adds the bias, and writes it back again. Finally, a third kernel launches for the softmax. This constant round trip to global memory starves the GPU. The authors of the ScaleFold paper fix this by writing custom kernels using the OpenAI Triton compiler. Instead of separate steps, they fuse the entire sequence into a single kernel. Here is the key insight. By fusing the operations, the GPU loads the input data into its fast on-chip SRAM just once. It performs the matrix multiplication, adds the pair bias, applies the softmax, and does the final multiplication directly inside the SRAM. It only writes to global memory when the entire multi-head attention block is finished. Standard optimized libraries like flash attention do not work here because of that unique pair bias injection, making a custom Triton kernel strictly necessary to bypass the memory bandwidth bottleneck. This approach extends to other fragmented parts of the model. LayerNorm consumes 14% of the step time because AlphaFold uses small dimensions, typically 128 or 256. When using dynamic axial parallelism, or DAP, these problem sizes are scaled down even further, leaving the hardware underutilized. ScaleFold introduces a fused LayerNorm kernel where a single CUDA thread block processes multiple input rows at once. It calculates normalization statistics in a single pass rather than using expensive iterative methods, and it uses a two-step reduction in the backward pass to avoid atomic operations. Even the optimizer gets fused. The ScaleFold authors combined the atom optimizer and stochastic weight averaging into one single kernel. Intermediate values between the optimizer steps stay in GPU registers, bypassing memory reads completely. For the rest of the model, they rely on PyTorch compiler tools to automatically fuse the remaining fragmented operations, particularly in serial components like the structure module. When you're dealing with thousands of small memory-bound operations, your bottleneck isn't teraflops, it's memory bandwidth and CPU launch overhead. Fusing those operations into single continuous blocks of execution is the only way to actually saturate the hardware. Thanks for listening. Happy coding, everyone.